All right, so we're going to start with page 56, number 4. So page 56, number 4, there's lots of stuff going on there. Okay, so the first thing they do is they give us a height versus time function. So S at t is equal to negative 5t squared plus 180. All right, and t is in seconds, h is in meters, or I guess s is in meters since that's representing the height. And at first they're asking us to find the average velocity during each of the first 2 seconds. All right, so real quick here for A, so the first second, all right, would be between 0 and 1. So here t is in the interval 0 and 1. So I don't know if I'll do both of them because they're going to be essentially the same. So what we're looking for here for the average rate of change, remember, is equal to the slope of the secant line, which is just given by s at 1 minus s at 0 all over 1 minus 0. In other words, the difference in the y values in this interval over the difference in the x values. So in this here, what do we have? S at 1 would be negative 5 plus 180, so it'd be 175. Oops. 175 minus s at 0, well, it would just be 180 all over, well, 1, obviously. And so here, negative 5. Now, because this rate of change has a meaning, okay, we really should be including that this is meters per second. And we shouldn't be surprised that we get a negative answer because they're saying that it's a falling object. All right. So for the second, you would just be doing t goes from 1 to 2, and you'd be doing the same thing. So I don't think it's necessary for me to write that one out. So let's take a look at what B is asking for. B says find the velocity of the object when t is equal to 4. Okay, so at this point here, you know, we've got lots of options. Okay, so they're not clear as to whether they're looking for an approximation, whether they want us to do it using the limit definition, or where now we can use our derivative properties to use the derivative to find the rate of change. Okay, so here again, it all depends on how the question would be asked. All right. So let's say, you know, just to get something under our belt, let's say doesn't say determine an approximation, but let's do it using limit. Let's pretend we don't have those new derivative properties that we found for polynomials. So here, if I was looking for the velocity of the object at t equals 4, well, we know that that would be the slope of the tangent at t equals 4. And that's given by the limit as h approaches 0 of s at 4 plus h minus s at 4 all over h. Okay, so this is how we hopefully can find the exact rate of change at that value. So here, limit as h approaches 0. So what do we have? Let's put 4 plus h in here. So negative 5 times 4 plus h squared plus 180. Okay. And then we're subtracting s at 4, which would be negative 5 times 4 squared plus 180. Okay, all over h. Okay, so the first thing I notice is that the 180s are going to cancel out because I've got 180 minus 180. Okay, so again, please keep track of my algebra here. So this is negative 5 times. So square the first, square the last, twice the product. So 2 times 8, h plus h squared. And this is going to be plus, what do we have here? 16 times 5. So 50 plus, my brain just went numb. What is 16 times 5? It's 50 plus 30, 80, right? Somebody confirm that? Confirmed. Okay, and so now limit as h approaches 0 of, I guess this is also going to be minus 80 minus 40h minus 5h squared plus 80 all over h. So these constants cancel out. I can factor out an h, or I guess I can even factor out a negative h if I wanted to. Let's just factor out the h. Okay, so what do we have here? Negative 40 minus 5h. And there we go. And so now at this point that we've reduced the h's, we should be able to determine the limit. And we see that this part here goes to 0. So it's just negative 40 meters per second. Okay. And we shouldn't be surprised that this value is further from 0 than the original value in the first second. And I think in the second it's something like negative 15 meters per second, because obviously as it falls, it's gonna increase in speed. All right, any questions so far? Okay, so now for C, they're asking for the velocity when the object hits the ground. Well, you know, they didn't tell us when it hits the ground. So I guess we're gonna have to do is we're gonna have to calculate that first. And where does it hit the ground? Well, at the time that the height is equal to 0. So I just have to solve negative 5t squared plus 180 equals 0. So 5t squared equals 180. T squared is equal to, so that's going to be 3. And what am I left with? I'm left with 30. So it looks like that's going to be 6. So 36. So t is going to be equal to plus or minus 6. Okay. But since we know t has to be greater than or equal to 0, we're not interested in t equals 6. Okay. And now just to change things up a bit, and because I don't want to do this whole rigmarole with the limit, let's now use the fact that I can find the derivative function using my derivative properties. So what are my derivative properties? So I probably wouldn't have to do this on this test, okay? But just to save ourselves some time, we might as well do it this way, okay? Well, I know this constant of negative 5 that's multiplying the t squared. I can just remove that and work just with t squared. So I know that the derivative is going to be negative 5 times what's the derivative of t squared? Well, we know it's 2t, okay? And then I know that the derivative of sum is the sum of the individual derivatives, and the derivative of 180, hey, that's just a constant. So that's just like plus 0. So if I want to find the rate of change at the time when it hits the ground, I just now have to, oops, I'm just going to put 6 in there. So what do we have? Negative 5 times 2 times 6. So it looks like it's 5 times 12, negative 60 meters per second. Okay. So by the way, you probably wouldn't be asked to solve this problem this way, but like I said, there was no point in me redoing another limit. But this kind of gives you a sense of how we're going to use these derivative functions. All right. Any questions here?
Yeah, so I'm just curious, are we gonna have to do or like memorize the derivative functions for this test this Tuesday or not?
Well, essentially, you know what the derivative of x to the n, you should know that. You should know
Okay.
that the derivative of, a constant is 0.
Okay.
Yeah, so you might be that they would be very simple ones, but yeah, like I would expect you know that the derivative of x to the n is n times x to the n minus 1, because
Yeah.
I did
Okay.
say it was going to the first page of lesson 7. Okay, so anything up to the first page of lesson 7, you would be expected to know.
All right. Thank you.
Okay, great. Anything else? No. All right. Let us move on to 56. Let's go to 9C. So find the values at which the function is discontinuous. Find the limits of those values if they exist. It's kind of a badly posed question. I think I know what they're asking for, but I will agree it's not the best posed question in the world. So page 57, okay, and in a sense we have to do A in order to do B. So let me just write down this function. Oh, sorry, page 57, number 9. Okay, so we have x plus 1 if x is less than -1. We have negative x plus 1 if x is all between -1 and 1. And then lastly, x minus 2 for x greater than 1. Okay, so when I take a look at this function here, I notice that each individual part is a polynomial. So I don't really need to worry about any values other than when there's a change in the equation of the function. So the only time I really need to, do any work here is at -1 and at 1. And so we want to determine if it's discontinuous anywhere. All right. And if it's not discontinuous, let's find the actual limit. All right. So the first thing I noticed is that this function is not defined at x equals 1. Okay. So right off the bat, I can figure out, or I can determine that at x equals 1, it's not continuous. So x equals 1, f not continuous, since f at 1 does not exist. Okay. Now you see how, by the way, also how short and sweet everything is here. I'm just saying what the result is, and very clearly, as soon as it doesn't exist there, so there's got to be, like either a hole, whether there's a jump or not, f at 1 doesn't exist, it can't be continuous. Now it is possible though that it may have a limit. So this is what we're going to check here. So I'm going to check the limit as x approaches 1 from the left. Okay, so I know it's not continuous, but it may still have a limit. So from the left, so to the left of 1, less than 1, I'm going to be using this function here of -x plus 1. And what's that equal to? Again, this is just a polynomial, so it's going to approach the function value. So -1 plus 1 looks like it's equal to 0. And let's approach x from the right. And when we approach x from the right, I'm going to be using this function here that give me the y values to the right of 1. And so here again, what do we have? We have 1 minus 2 is -1. So what we see here is it's not continuous at 1 because it's not defined there, but neither does it have a limit. So f has no limit at x equals 1. Okay. So discontinuous, we answered B. C, discontinuous there, and it doesn't have a limit. Okay, so somebody asked, why is it not defined at 1, but not at -1? Well, because here we see that when x is equal to -1, it has a value. Okay, I'm not sure if it's continuous there, but it has a value. Where if you look at 1, x equals 1, well, there's nowhere here that shows it ever being defined at x equals 1. It's defined for x less than 1. It's defined for x greater than 1, but never at 1. Whereas at -1, well, here it's defined for x less than -1, but in this middle scenario, it's actually defined for x greater than or equal to -1. Okay, so that's why it's defined at -1, but nowhere is it defined at +1. Okay, does that answer the question? Okay, great. So now let's test the other place here where just because it's defined at, you know, -1, there's no guarantee that it's continuous there. There could be a jump. So the first thing I'll do is I'll test f at -1, which is given by this function here. So -1 plus 1 is equal to 0. So now let's take the limit from both sides. So the limit as x approaches -1 from the left, okay, is equal to, the left would be this, so x plus 1. So here we have, oh, why didn't somebody stop me here? I made a mistake. Take a look here as I erase. Take a look at what mistake I made. Very silly. Okay, and it's that mistake that I always warn you folks about, is the sign errors. So at -1, it's defined as -x, so negative of -1 plus 1. Okay, so very important here to be very careful there. So that ends up being 1 plus 1 is 2. Okay, so I missed the negative, caused the problem. All right, so now as I'm taking the limit to the left, let's go back here. Well, it's approaching using this function. So -1 plus 1 is 0. And if I take the limit as x approaches -1 from the right, well, we kind of already did that already. It's going to be this function here. And that's going to be approaching -1 plus 1 is 2. So even though f at -1 is defined, okay, f is not continuous. Okay, f is not continuous at x equals -1, since f does not have a limit. At x equals -1. Okay. So here, they didn't really say explain, but I thought this was a good opportunity to practice to make sure we understand why it's not happening. So here, it's not continuous because the function's not defined there, but it does have a limit. Here, this function is defined at -1, but doesn't have a limit there. Hence, it can't be continuous. All right. So, a few things going on in this one here. Any questions on this one before we move on? No? Okay, so let's go to 11b. 11b. So it tells us to consider that function for what values is f discontinuous. So that's A. So let's take a look at B. At each point where f is discontinuous, determine the limit of f at x if f exists. Okay. So we have a function. So this is page 57. We'll just say number 11. So the function is f at x equals 2x minus 2 over x squared plus x minus 2. Okay. And this is a rational function. Now, based on what we know of rational functions, and we think about our definition of continuity, a rational function is unlikely to have any jumps, but for sure, we know could have holes and it could have vertical asymptotes. So this is what I should be looking for if I'm looking for discontinuities. All right. So of course, we know that when we're working with rational functions, the best thing to do here is to, I'm just going to make that a little clearer. Okay, the best thing to do is to factor, and then that's going to help us see these characteristics more easily. So here we have 2 times x minus 1, and then here we have x plus 2x minus 1. And so what I see here is that there's a vertical asymptote at x equals -2, and we have a hole, because the x minus 1's cancel out, at x equals 1. So these are the two values. So this essentially solves A. Okay, this is where the function is going to be discontinuous. Okay, Now, at which value does it have a limit? Well, if we're answering B, we can say limit does not exist at x equals -2. And that's because, well, there's a vertical asymptote. Since I'll have to, you know what? I'm going to show you I'm going to show you some nice notation another day to save ourselves a bit of writing, but I won't do that here because there is a vertical asymptote at x equals -2. Okay, but there's a hole here, and the nicest way to show that is to take the limit. If I take the limit as x approaches 1 of, and I'll put it in factored form, I see that because these reduce, remember, we don't care what happens at 1, this becomes the limit as x approaches 1 of 2 over x plus 2. And so the limit does indeed exist, even though the function's not defined there. And it would be, so looks like 2 over 1 plus 2, looks like it would be 2/3. Okay. So here, there was nothing to do because there's a vertical asymptote, limit cannot exist. Whereas here, because we have a hole, we can take the limit and it still approaches a particular number, even though it's not defined there. All right, any questions on this?
I have one quick question.
Yeah.
So do we not write for 2, right? Do we not do limit of as x approaches -2, f of x is equal to infinity or positive or minus negative infinity? We don't have to do that?
I wouldn't say that it's a necessity here because a vertical asymptote is a discontinuity. And we also know that a vertical asymptote, at a vertical asymptote, a function can't have a limit there. That's one of those scenarios where the limit does not exist. Where a hole, we know that the limit could exist there. In this case here, because it's approaching the same number on either side, because there's a hole, the limit might still exist. Okay. So at a vertical asymptote, no continuity, no limit. At a hole, obviously we know it can't be continuous, but in this case here, because it does have a limit, it satisfies that.
So there's no need to indicate if it approaches negative or positive infinity.
Not unless they're asking for that. No.
Okay, and then if they ask for it, then it's okay.
Yeah, for sure. So if they ask you, describe the behavior near the vertical asymptote, then you would be expected to say that. Okay, good question. All right, so I think we're on to our last one here. Oh, wait, no. Oh, yeah, this is our last one of this section here. So 17B and E. So 17C does have a video to it if you are interested in that one. Did I give B? Did I assign B?
I asked for it, Tony, but then I realized that it wasn't even assigned. So
okay,
sorry.
it's let me give you just a quick tip on that. If you take a look at it, do you not notice that those two expressions have something very nice going on with them? And if somebody's got a textbook in front of them, look at page 59, number 17B. I just kind of didn't put it, but you should be able to do. What do you notice about those two expressions? X plus 4a squared, 25a squared. I'm hoping people notice that that is a very special, combination with a subtraction in between. Oh, it's more than good numbers. You need to, they're not perfect. Well, each term is perfect squares, so it's a difference of squares. Okay. So what I would do is I would rewrite 25a squared as 5a all squared, and you should be able to factor. Okay. So if you want to, like I say, sometimes people are looking for extra ones as practice, you might want to do 17b. But did you get what I was aiming at, Maya?
Yes, thank you.
Perfect. All right. Oh, sorry. It's x approaching 0. I'm so used to h. And we have 1 over x and 1 over 2 plus x, and then minus 1 over 2. Now, I suspect this one, although I think there was one similar in the homework, something like this sometimes might throw you off because it looks a little different from what, sorry, this is 17F. It might just look a little different, but can you see that multiplying something by 1 over x is the same as doing what?
Dividing
s-
by x.
Yeah. Oh, sorry. Was it E we asked for?
No,
Oh,
you're
yeah,
good.
it was. Yeah,
Or-
E. So I'm doing F. I'll do both. I'll do both. Yeah, sorry about that. I might as well just do this quickly. I just realized. Sorry about that. Oh, yeah, might as well do it. Okay. It's just like dividing by x. So here, when I look at this here, this is causing the problem. So I'm hoping that doing some algebra here will help me deal with that. Okay, so sorry, we'll do E in a second. Okay, so I'll do this quickly here. So it makes sense to subtract these. So 2 minus, and this, folks, is the big, make sure you're putting those brackets there. Otherwise, very good chance you might make a silly error. Okay, and here 2 minus 2 cancels out. And so what are we left with? Oh, so used to do an H. Okay, 1 over x. And what are we left with in the numerator? Minus x. And so there we go. Those cancel out. And now we can determine the limit. So what's happening here? We have a -1 in the numerator. And this is approaching, well, 2 plus 0. It's approaching 2 plus 0. So 2. So it looks like -1 over 4. Okay. So let's do E, which is the one that was actually asked for. Okay. E's limit as x approaches 4. Okay. And again, when I look at E right away, my brain should be telling me to do something. Okay. What should my brain be telling me to do?
Rationalize?
There you go. I mean, really, like I said, when it comes to the square roots, it's really the only trick we have up our sleeves. Okay. So I'm not even going to question it. I mean, first of all, you should always check. The denominator is approaching 0, but there's only a point in rationalizing if the numerator also approaches 0, because if the numerator approaches 17, I don't need to rationalize. I know it doesn't exist. So let me just check quickly. 12 plus 4 is 16. Square root of 16 is 4. 4 minus 4, 0 over 0. So yes, I'm going to have to rationalize because this thing has a shot at existing. Okay, so always a good idea to check because you might be doing a lot of work for nothing. Now, one thing I want to remind people of is the reason for rationalizing, at least in this problem, is to do algebra in the numerator. Okay, number one. And second of all, the goal is hopefully to cancel out this x minus 4. Okay, so please, yep.
I'm so sorry to interrupt, but I think a couple students and I realized that you have to do 4 plus root 12 plus x on the right hand side. Because
I put minus. Thank you. Yeah. Good
welcome.
catch there. Good catch. Thanks for noticing that. Okay. Thank you. Okay. So what I was saying is, please don't bother distributing the denominator. I think it was in the quiz where a lot of people were distributing the denominators, and it just overcomplicates things for no reason. Okay. So I would suggest it's the numerator that I'm doing this for. So let's go ahead and do that. So here we have 16 minus, again, please don't forget the what was I going to say here? Please don't forget the brackets here. Otherwise, risks kind of not being very nice. Okay, so here, like I said, in the denominator, I'm not touching anything because I'm hoping that x minus 4 is going to cancel out. All right, and so let's see what we got here. Limit is 8x approaches 4. So here, I'm going to put the x first because, I'm hoping it's going to look something like this. So here I have negative x, okay, and then 16 minus 12 is 4. And, if I kind of don't think about it too much, I might start panicking a bit because I didn't end up with an x minus 4 in the numerator. But of course, what can I do? That will make everything work out here. Well, yeah, is it Zavarier, or was that the hand from before?
Yeah, no, that's the hand for
Yeah.
now. So you can factor out the -1 in the numerator, and then
There
the
you
x
go.
minus 4s will cancel out, and life is pretty much simple because
There
you'll
you
have
go.
1 in the numerator. Or
Exactly.
-1 in the numerator, I should say. Sorry.
Yeah. You know, and sometimes that's why in a question like this, where you kind of know, one of those times where you do know where you're hoping it's going to go, which is to get an x minus 4. Hopefully you think of doing that. Now, by the way, do you see that if you had not put the brackets here, you would have probably ended up with something that wasn't going to work out at all. Okay, so it's really important, that those little details in the algebra are done with care. So here, now I can evaluate the limit. So it looks like -1 in the numerator. And then here, what do we have? We have 4 plus, and this is 16. So square root of 16 is 4. So it looks like we have -1/8. Okay. Any other questions on these here? Nope. All right. So let us move on to, we can now move on to page 60, number 6. Page 60, number 6. And so what we have here, it says determine the slope of the tangent at x equals 4 for the function f at x equals x over x squared minus 15. X over x squared minus 15. Now, by the way, I'm looking at this and I'm already thinking, might be a little more, complex in terms of the algebra. So this is where, I'm going to put my mind to getting that first expression correct so that I can then focus all on the algebra. So if we're looking for the slope of the tangent here, okay, that's the limit as h approaches 0 of, and let's, let me be really careful here. Oops, it's at 4. Okay, let me put the definition right on so I can then follow it. So 4 plus h minus f at 4 all over h. And now let me very carefully input everything so that, I'm starting off on a solid footing. So here we've got 4 plus h over 4 plus h squared minus 15. Okay, minus f at 4. And I'll calculate f at 4 here so I don't have to waste another line. All right, so what do we have? We have 4 over 4 squared minus 15, which actually works out pretty nicely because it's just 4 over 1. So there we go. And of course, all over h. So we got, we got kind of lucky there. We got a nice number to work with. So here I'm going to have to subtract using a common denominator. So 4 plus h minus 4 times. Now this is where, I feel comfortable enough to start, saving myself some time. So why don't I expand this while I'm at it? So this is going to be 16 plus 8h plus h squared minus 15. Okay, all over the common denominator, 4 plus h squared minus 15. And of course, I know that dividing by h is like multiplying by 1 over h. So that h is just going to end up in the denominator. So if you're not comfortable going from here to there, you might want to add one extra step. Okay, or maybe actually write out the times 1 over h. Don't take any chances if you're not 100% confident in doing what I just did. Okay, so here we just have to clean this up as much as we can. So 4 plus h minus, so this is 16 minus 15 is 1. So it's going to be minus 4. Then minus, this looks like 32h, and then minus 4h squared. Of course, please check all my algebra. And then what do we have? The 4 minus 4 goes. So here, I think it's worth writing out an extra. So what do we have? We have h minus 32h. So it looks like that's negative 31h plus, minus 4h squared over this whole big thing. And now, again, I'm going to feel confident enough here to see that this h is going to cancel out. So, I'm factoring out an h, so one here and one there. So what are we left with? I'm left with, in the numerator, negative 31 minus 4h all over this whole thing, 4 plus h squared minus 15. Okay, so as long as I didn't make any silly errors here, we can now evaluate this limit. So the numerator, this approaches 0. So I'm left with negative 31. And then in the denominator, this is approaching 0. So 4 squared 16 minus 15 is 1. So it looks like this is approaching negative 31. Okay, so quite the journey. Okay. But in the end, you see how once we had this down, the focus needed to be purely on the arithmetic. Okay. Okay, any questions on this here? Oh, all right, let us move on. What's next? So we're done that. So we're going to page 74, number 19, 74. So 74, number 19. Oh, so Zavarier, is that a new?
Is my hand up accidentally? Oh, sorry,
Yeah,
my bad.
it'll be there. Okay, so we have Callan is asking, what if you take the derivative and then put in x equals 4 later? At this point here, we have not determined how to take this derivative. So, it's not something we've established that finding derivatives of something like this. So no, that would not be acceptable on this test. Okay. Writing notes. Yeah, you can keep forgetting to talk about that. Yeah, I should send out an email that you can keep handing. I had an idea that I thought I was going to do something different with the notes, but I think I'm not going to do that. Okay. Where were we? Page 75, number 19. Okay, so this one here says, at what point on the graph of, let me write that down, x squared minus 4x minus 5 is the tangent parallel, that's my symbol for parallel, to, where am I, 19? 2x minus y equals 1. 2x minus y equals 1. Okay. So, this is where, as I said, I expect we have to be able to use anything that we've learned from grade 9 to grade 11. Those are all courses that lead up to this one here, actually to grade 12 advanced functions. And so what can we glean from this? That the tangent we're looking for is parallel to this line. So what is that telling us essentially about this tangent?
They have the same slope.
They have the same slope. So we know that two lines that are parallel have the same slope. So step number one, obviously makes life a little easier to write this in slope intercept form. So bring the y to the other side. So 2x minus 1. So the slope of our tangent line needs to be the same as the slope of this line here, which is 2. They could ask you, what does it take for it to be perpendicular? You need to know what it means for two lines to be perpendicular in terms of their slope. All right. So again, this question would likely have been assigned when we didn't yet have our derivative formulas. So let's solve it that way. Okay. So here, what we need is we need to determine where this function has a slope, a tangent equal to 2. So what's our process for finding the slope of the tangent at a point? Well, we have our limit definition. So what I know is that the slope of the tangent is given by the limit as h approaches 0 of f at, well, whatever my value is, okay, a plus h minus f at a all over h, okay, except it's not the a value that we have and the slope of the tangent that we're looking for. It's the slope of the tangent that we're given, or at least, indirectly given. And so now I'm going to have to figure out what a value gives me this. So hopefully this will create an equation that I can solve. Okay, so this a value or x value is the thing I don't know at this point. So I'm going to put this into the limit and hope this all works out, which now we've kind of seen should work out pretty nicely. So let's put a plus h. So a plus h squared minus 4 times a plus h minus 5. Okay, and then subtract f at this unknown x value, call it a. Okay, which is a squared minus 4a minus 5. By the way, I'd have no issue if you used x instead of a. Like I said, I'm just using the notation that we would have been using at the time that this would have been assigned. Okay, now I just gotta, it's gotta see everything through. So this is a squared plus 2ah plus h squared minus 4a minus 4h minus 5 minus a squared plus 4a plus 5. Okay. Whoops. What did I forget here? Bad notation. Forgot my limit as a approaches 0. H approaches 0. So let me just add that in. Okay, so it's kind of always good to kind of evaluate your expression. That's what I did as I looked at it and I saw something's wrong here. And I realized that's what it was. Okay, so as probably should have expected, a lot of these things cancel out. So the a's squareds cancel out, the 4a's cancel out, the 5's cancel out. Okay, and everything that's left in the numerator has an h in it, as we kind of hope would be the case. So let's take out the h, and what do we have here? Well, we have 2a, okay, plus h minus 4, and that's everything, which cancels out with the h. Okay, now by the way, knowing what we know now about taking derivatives and our derivative rules, you should know that this is exactly what I would be expecting. 2 times the x value, okay, because that's the derivative of x squared, minus, well, what's the derivative of negative 4x? Well, it would just be the slope there, negative 4. So this should not be surprising given what we've seen. So we have 2 is equal to, so the 2a and the 4 don't change, but the h approaches 0. And lo and behold, we have a nice, easy equation to solve for a. 2a equals, I guess this is 6. So a is equal to 3. So this function at x equals 3 is going to have a slope of 2, parallel to that line there. Okay. So I hope you can see that now with our new powers of our derivative rules, this question becomes much, much, much easier because I don't have to go through this whole process of always using the limit definition. Yeah, Zavarian?
In the event you want us to use like derivatives for this y is equal to x squared function, is it okay if we can, I'm assuming it's expected that we use the d by dx of each term such that finally we're able to find the value of a, correct?
It all depends on how the question is posed. So I have to say that on this test, I would probably ask you to use the limit definition to find derivatives for the most part.
Got it, thanks.
Because that's been our main focus. Now that we start having these powers and we're going to start developing a lot more, then in future tests, we will be using the limit definition much, much less, you know, and eventually not at all. Okay. But given that this was the crux of what we were working on, chances are it's going to be limits more than anything else. Yeah, Arthur.
We could have just used X instead of A, right?
Yep.
Okay.
Like I said, I was just using the slope of the tangent at a point, at a particular value. You know, when we were doing, you know, like I said, when this was likely assigned, we were probably still using A to represent a specific X value, but that would have been fine. Yeah. Ella?
Thank you.
Would it be wrong if we used, like, to find the derivative, we didn't use a limit definition?
It depends on how I pose the question. So if I don't give you any conditions, then you do it. Well, the only thing I would say I wouldn't accept for full marks would be an approximation. So that would definitely not get you full marks because there are ways. But if I specify that the limit has to be determined, as the derivative has to be determined using limit definition, then obviously you wouldn't get full marks for using the limit properties. Okay, so that's why you want to read the questions very carefully. All right, anything else here? All right, I think we've got, I think it's one more. So now we're going 197, 16D, 197, 16D. Okay, so here it says determine equations of any vertical horizontal asymptotes for each function. Describe the behavior of the function on each side of any vertical or horizontal asymptote. So this was D. So this is y is equal to 2x squared plus x plus 1, 2x squared plus x plus 1, all over x plus 4. Okay, so they said horizontal and vertical, right? Okay, so let's start with, I guess, vertical asymptotes. In this case here, certainly easier. Okay. So we see that there's a vertical asymptote at x equals 4. Now, why can I say for sure that this is not a hole? I kind of did a little calculation in my head that told me right away that this has to be a vertical asymptote and not a hole. Yeah, Zavaria?
Because you can't really break up the 2x squared plus x plus 1 such that one of your factors is going to be like x plus 4 or something like that. And
Okay.
if you just take it overall, you can't really determine that there's any holes present.
That's it. Is this doesn't look like it's factorable to get an x plus 4. And actually what I did in my head is I did good old b squared minus 4ac, which is the interior of the square root of the, what do you call that, quadratic formula. 1 minus 4 times 2 times 1 is less than 0, which means this doesn't have, yeah, good old discriminant. This doesn't even have any real roots anyways, okay? So regardless of what sort of reasoning you use, you realize that this can't have a factor of x plus 4 in the numerator, okay? This shows can't have any factors, okay? So in the end, this is what we're using. And I did notice in the assignments that I was looking at today, a lot of people did not use limit notation on these questions in this area here, which I had specifically said was the point. So it will be very clear on the test that you have to use limit notation. And so if you don't, you know, you wouldn't get full marks for it. Okay, so here, if I'm looking to describe the behavior around the vertical asymptote, I'm looking to the left and right of the vertical asymptote. Okay, so what I want to determine is the limit as x approaches -4. Also, how come nobody corrected me there? You should have corrected me. Come on, it's -4. Okay. From the left, I guess it's y, and then the limit as x approaches -4 from the right of y. Okay. But I would say you should show me a little bit of work to tell me to show me whether this is going to positive or negative infinity. And the idea here is that I can use the old number line. So I've already shown that the numerator is never equal to 0. So I actually don't have to worry about that. Now, the reason you might say, well, why do I have to worry? I'm just going to take take say -3 and -5. Well, what if in between -4 and -3, there's an x-intercept? It could change sign there. So you do have to be careful. But in this case here, I've actually already showed there's no x-intercepts because the discriminant is negative. So that means the only place this thing can change sign, if it does, is at -4. So let's try -3 and let's see what happens. So let me try to do this carefully here. So this is going to end up being 9 times 2 is 18 minus 3 is 15 plus 1, so positive in the numerator. Notice I didn't care what the actual result was. And in the denominator, well, -3 plus 4 is also positive. So we've got positive here. And now let's take -5. And I kind of realized, well, wait a minute, if this thing has no x-intercepts, it means it must be, if it's positive on one side, it must be positive everywhere. Let me just check it here. 2 times 25 is 50 minus 5 plus 1. Yeah, definitely positive in the numerator, but in the denominator, -5 plus 4, negative. So that means it has to be negative to the left of -4. So that tells me that when I approach -4 from the left, okay, so you really should be showing this work, means the function has to be negative, so it must be approaching negative infinity. Whereas to the right of 4, since the function is always positive, it must be approaching positive infinity. Okay, so this is the notation that I expect to see to give your answer. And the work is, well, that work we've done in the past for checking the sign of the function. Yeah, Sadie?
So for questions like these, would it be incorrect to plug in like -4.01 and -3.99 and then see what that is? Like, do you want?
Yeah. Well, which is essentially what I'm doing here. I kind of, saved myself some time by kind of just quickly, just because I would rather put in -3 and -5 if I can. But yeah, that also makes sense. Again, you have to be careful. What if what if you put in -3.9 and there's an x-intercept at -3.99? Then it could have changed sign in between. It's unlikely, but that's why it's not a bad idea to kind of also check the numerator, make sure there's nothing funny going on there. Okay, does that make sense?
Yeah, it does. Also, one more question about this. If there were to be a horizontal asymptote, what would you plug in then to find out the behavior?
Okay, so in this case here, I guess unfortunately there's no horizontal asymptote. So here, no horizontal asymptote, so we don't have to answer that question. But let's say this was, so first of all, if it's something like this, well, the horizontal asymptote is y equals 0. So you could use the same idea here by just checking the sign of the function. The issue becomes, let's say you have something like this and your horizontal asymptote is y equals 1. Okay, so this is where the easiest thing to do is to take some really, really big number, some really, really small number on the other side, something, take like 1,000,000 on one side and -1,000,000 on the other side, and see, is the function just slightly bigger than 1 or is it just slightly less than 1? So if it's a little bigger than 1, it means it's approaching 1 from the top. And if it's slightly less than 1, then it's approaching from the bottom. Okay.
Yeah,
so that's kind of a good quick way of checking. All right. So that was all the questions I was either sent by email or asked here. Anything last minute that we thought of that we want to ask? Arthur?
I have a question about this question number 16D right here.
Yep.
How is it on the left side? It's -5. Like, how is it still become negative?
Well, because here, the numerator, when I stick in -5 here, -5 squared is positive 25 times 2
Yeah.
is 50, minus 5 is 45, plus 1. Oh, it's positive in the numerator. And in the denominator,
Oh.
-5 plus 4 is a negative number. So,
So we
positive
don't
dividend-
simplify the expression. Because if you simplified it, then it'll be I think it would be 4x plus 1 over x plus 4. I think it would be.
4x plus 1.
I don't know. The thing is, I could be wrong. So
Well, yeah, because there's no like terms here, so you can't really simplify the numerator.
yeah. I mean, I did quadratic formula, so probably.
Okay,
the
but
reason why.
quadratic formula should have showed that there's no x-intercepts.
Yeah. Yeah, I
Yeah.
think I went wrong
So
somewhere.
maybe you just forgot a negative somewhere. Maybe you forgot this.
Yeah.
Yeah. Okay.
I think you.
Okay. Anything else for this one here? Or anything else? All right. So I am going to stop the recording. And well, 5:59. I guess these things always end up lasting an hour.